All right, everybody, how's it going? Welcome to our second lecture of week one here. Um, Yesterday, we talked a little bit about sections one, two, and three from chapter five, which are review-ish for some of us, most of us. So kind of the point is we're all just trying to kind of get on the same page this week. Some of us have probably a lot of work to do to get to where we need to be to start this class. Some of us have already essentially covered most of the topics being discussed this week and are just getting this as review. So that's kind of why I'm going through this stuff a little bit quicker. But we don't worry, we won't be covering entire chapters in a week any other point this semester. So this is just while we're getting into the swing of things here. So um, today we're going to look at sections 5.4 and 5.5. We're going to do a bunch of problems from each of these sections here, but we fortunately did already talk kind of a bunch of concept stuff from 5.4 actually already last class here. So as I'll do all semester, I'm going to be kind of picking up the highlights here of what we should be doing. You guys certainly should have been doing the reading before and anyway, so I expect that you guys already have some familiarity with these things. Um, so first things first, in section 5.4 here, we are looking at our indefinite integrals and the net change theorem. We talked some indefinite integrals yesterday. We'll do some more today. We essentially, I don't know, net change theorem, I guess, is a statement about applications of integrals here. All it is just a little argument about units that's very, very easy. And the book does a really good job with the net change theorem of stating it as examples rather than trying to state it formally and hoping you get something out of it. So just some highlights from this 5.4 section. On page 406, there's a table of indefinite integrals, but the important thing for you to see in that table is if you just read every equation sort of backwards, then in a sense it's just a derivative table right there. Uh, oh, Chris, yeah, 5.4 and 5.5. Okay, so yeah, you're right. I gotta throw those homeworks up in my open math there. I'll probably do those this afternoon or tomorrow morning for the 5.4, 5.5 homeworks. But yeah, I gotta make those here. Thank you for reminding me right there. Page 407, an example five. This is just one thing I felt was worth pointing out right here. This is one of those ones, example five on page 407, that I see people get stuck when they shouldn't. This is a good example from this section that is your reminder. So you should go read this example. But just look in there. The lesson to be learned from this example is remember, you should always be doing algebra before you do calculus when at all possible. Since calculus is harder than algebra, we always want to use algebra to simplify expressions as much as possible first, then do the calculus step. So that was just an important little thing to remind you there of that example. And then finally on page 408, the net change theorem. I really like the way that the book states this because the formal statement of the theorem is not exciting. The purpose of the theorem, understanding some applications behind the net change theorem is what's really important. So after they state the net change theorem, they give 8 examples. And they're not stated as examples like example 1, example 2. They're more like bullet pointed examples. But they're just like, here's a whole bunch of different contexts we can reference this in. They talk about oil spills. They talk about economics. They talk about physics. They talk about just a whole chemistry example. Like they give a little sample of like, how does the net change theorem apply to like all these different things? And so I think that those examples are really good. I really appreciate it when the book uh, does slightly less formal definitions for things because I feel like formal math definitions rarely help us conceptually. They usually help us with formalities, but if we're trying to learn concepts, I think those are better done through examples. So I really like the way that the book kind of laid out the net change theorem stuff. So make sure you read those examples. Like those words are, in a sense, the most important thing from this section is like feeling out the words that are associated with each of those examples that are right there. So all I really want to do right now is walk through a bunch of examples. You can see I've got a bunch of numbered problems here. These are some like homework problems, some of the kind of like tougher homework problems that I found that I liked from the textbook here. So I kind of just want to walk through some of these as our kind of 5.4 stuff, do some examples here, and then we'll talk about U sub. The U sub stuff we'll have to talk a little bit more like actual concept for rather than just execution. But for these, I think that this is a little bit more of just like a practice thing. Continue to get into the groove of performing integration and thinking about how integration is related to a Riemann diagram. So find the area in the first quadrant bounded by the curve x equals 2y minus y squared. So I am guessing that the first thing that you see here that bothers you is the same first thing that bothers me, which is that this is an equation that is not in terms of y equals, but is rather in terms of x equals So I want to think to myself, what do I think this looks like? I think like kind of drawing a graph is certainly our most important thing that we could do first here. And the thing that I'm noticing first is that it looks like this is factorable. Uh, and so it does look like so typically we talk about roots where roots are x-intercepts, but here it looks like these roots should be our y-intercepts. So it looks like I'm seeing that we should be getting y-intercepts at y equals 0 and at 2, right? So I can do a little factor. I can see where my y-intercepts are. They're y-intercepts because x is 0 when y takes on the value of 0 or 2. So whatever my graph looks like here, I know that I'm hitting the y-axis at 0 and 2. The problem tells me that I'm only interested in accumulating some area in the first quadrant, so I'm kind of drawing my graph to be kind of first quadrant dominant here. And the thing that I'm thinking is that if we were to picture this graph, if we were to think about this flipped, right, if we thought about this the way that we might normally like to see this thing written, I would say that this is how I like things really. I like y equals equations and I like my squared term to be first. If this were the case, I know this would be a parabola that opens down, right? So this should be some downward opening parabola right there, and I know that because of negative x squared. So it opens along the negative y-axis. Since our x and y roles have been flipped, I'm picturing that our graph for this equation should also be a parabola because we're also looking at something that's quadratic. But we've switched roles of x and y, right? So if I'm doing my arm math here, if I switch roles of x and y, then we've switched where our axes are. This graph right here opens down along the negative x-axis, or sorry, along the negative y-axis is where it opens down. So I'm thinking this one should open along the negative x-axis, just like this one opens along the negative y-axis. So just kind of picturing my graph right here. I'm picturing that we've got, oh man, a sideways parabola is the most awkward thing in the world to draw. Okay, I'm picturing a sideways parabola like this. We're interested in the area in the first quadrant, so we're interested in this region right here. We want to know how much area is contained in this first quadrant piece of our graph right here. So what I'd like to do is I'd like to draw my relevant Riemann stick that's going to help me out here. So we've already identified that these heights are at y equals 2 and at y equals 0. And it looks like I can either draw for myself a vertical Riemann stick, but that's going to be tough because I can't quite tell where the bottoms and the tops of it are. If I were to instead draw myself a horizontal Riemann stick to help myself picture this kind of stuff right here, then I know that this Riemann stick is going to have a thickness of delta y because that change is happening in the y direction. That's our infinitely thin dimension. And what I know is that our integral should always represent an area computation, right? So I know that the integral is really the same thing as area, is really the same thing as length times width, right? We're always just thinking back to just rectangles for pretty much everything here. So what I need to have inside of my integral is I need to have a length term times a width term. If you're thinking in terms of graphical stuff here, length and width are just x and y. So in a sense, it's like I want to multiply x times y stuff in here. So I'm even going to write this as x stuff times y stuff. That's length times width to me, right? I want to add up all the lengths times the widths. Well, what is my x stuff here? Well, I know what x is. I have an expression for x. It's sitting right here. Y times 2 minus y. This is my representation of my x stuff right here, is y times 2 minus y. That's exactly what x is. What I need to multiply my x values by, all of those x values by, is the y values, the corresponding y values, because we're doing length times width, so x times y. I need to get my y values in here also, and so my y stuff is exactly our dy. This is our widths of each of our rectangles. So each of our rectangles here, top to bottom, has a thickness of dy. Every one of our rectangles has a left to right width of y times 2 minus x. And notice that what y times 2 minus x gives us, or sorry, I keep on saying this wrong, y times 2 minus y, what that computes for us is the value of x. That's our width, right? That is the total width that we're going to experience of each of these individual subrectangles. Finally, since this is a dy integral, I know that I need to give my lower to upper bounds of y values as my bounds of integration here. We have already solved for those to be 0 and 2. So it looks like this is my appropriate integral that's going to be associated with the words that were set up for me. So remember, drawing graphs is your friend. Doing some algebra to solve for some relevant values in the graphs is your friend. Do these things to help yourself out with these. Now that we're here, it should be relatively simple for us to go ahead and compute this integral. What I don't know is what's the antiderivative of this quantity in here. In general, when we're looking at polynomial type things that we're integrating, factored form is rarely our friend. Standard form is our friend in calculus, unfortunately. In algebra class, factored form is almost always your friend rather than standard form. But when we have to do integrals and derivatives, we'd rather see this stuff in standard form. So I'm going to go ahead and multiply this out. 0 to 2, we've got a 2y minus y squared dy. And we can integrate both of these terms. If I took the derivative of something with respect to y and got 2y, that something should have been y squared. And minus y cubed, this is going to give me a minus y squared, it'll give me a minus 1/3 y cubed. And again, I do so much of this stuff by guess and check. I really just give myself my essential component parts, my variable parts. I recognize that y squared is going to go to y cubed. Then I think, oh, the 3 would pop down. I don't want the 3 there, so I better put a 1/3 there to cancel it out, right? I kind of talk myself through the constant coefficient part and that subtraction. Just went along for the ride. Very important today is I am going to make sure that we are tracking our variables. That's going to be key for today. So don't lose track of what variable values those are. Those are y values. To evaluate this, I'm noticing that I'm going to evaluate this whole expression at 2 minus this whole expression at 0. Because I'm smart and I know that I'm going to do a lot of integration this semester, I want to recognize when I don't have any work to do. Notice that when we plug in 0 here, we just get 0, so there's nothing to do there. So all I've got to do to evaluate this entire quantity is just plug in 2 for y, because the parts that we plug in 0 go to 0. So it looks like I'm just going to get 4 minus 8/3. That's 12/3 minus 8/3, so 4/3 is what I'm getting for this guy here for that area that we have in the first quadrant right over here. So again, Riemann diagrams helping me think about this, remembering that integrals are just area and that's just coming from length times width. You just need to come up with a length component and a width component is all we're ever doing for our integrands here. I think this really helps me in figuring out what integrals we should be setting up and doing here. So there's our 43 right there. Now for 44, this one's going to be a lot like that one that we did yesterday where we did some funky switching of the bounds of integration, switching what variable we're integrating over. Maybe we should even do that as well today here. We can do this one both ways, certainly. I think I wrote this one out for myself both ways here, didn't I? All right, so find the area of the region bounded by, and I'm listing 3 different, or the book is listing 3 different bounding lines for us here. So as soon as the book starts giving you graphical descriptors, that is immediately the time for you to draw the associated graph. If it's giving you graphical descriptors and you don't draw a graph, you're crazy. Always draw these pictures for yourself. So I'm going to go ahead and draw my y-axis and my x-axis here. I don't actually know. Are we going to be only first quadrant here? I know that the y-axis will be a boundary for me. I've been given that the line y equals 1 is going to be a boundary line, so there's my y equals 1. I've got the curve y equals the 4th root of x. I know that the square root of x, Grave, I'll scroll back up here. So I'm still going to talk my way through this while Grave's looking at our last result there. So when I'm looking at this y equals the 4th root of x, I know that my square root of x graph is like my bent down. It's sort of like that sideways parabola. A 4th root of x is just going to be bent even a little bit more down right here. It turns out that the fact that there's a 4th root versus a square root is going to have incredibly little impact on how we think about this problem. There will be a 1/4 term instead of like a 1/2 term somewhere. But in any event, I'm picturing that the same type of square root curve for this guy right here. So drawing our oh great, did I make a mistake here? Evaluating, so he's asking if we're evaluating for 0 to 2, why isn't it negative 4/3? So in general here, when we get out our antiderivative, here we had that like f of y was the 2y minus y squared. Here I would say that my antiderivative, the book calls it the capital F. Yeah, I see what you're asking there, Grave. I'm gonna write that out here. So this capital F of y, our antiderivative, that's where we got our y squared minus 1/3 y cubed. And in general, when we're doing this integral then, if we do the integral of lowercase f of y from a to b dy, this is always going to be capital, the antiderivative f of b, the upper bound, minus the lower bound. And the way that I keep track of this one is just that, like, when we do things like delta t for delta time, that's always our time final minus our time initial. So it's always the antiderivative evaluated at the upper bound, which was 2, minus evaluated at the lower bound, which was 0 right there. So cool. Good question right there, Grave. I appreciate that. Keep those guys coming. Upper bound minus lower bound. Ah, yeah, yeah, yeah. All right, so sticking with our 44 here. So I've drawn my kind of crappy curve right here, but I'm thinking to myself, this appears to be my region of interest now, right? Here's the y-axis. Um, yeah, totally. Change. Change is always final minus initial. Yep. So we got our y-axis, we've got the line y equals 1, and we've got our curve. So it seems like this region that's in here, I just don't want to shade it in because I want to draw on top of it, but this region, this little somewhat triangular region right here, is the area that we're trying to come up with. And so it seems to me that it's possible that we could set up two different scenarios for this, right? It seems to me like we could either do this where we set ourselves up with some horizontal Riemann sticks to think about this, or set ourselves up with some vertical Riemann sticks to think about this. So I think we could do this one in both ways. I think it'll be okay. Some things I want to identify here on this graph is I know that no matter what I'm doing, I'm going to need to identify some bounds. It's pretty clear to me that since we're kind of, this graph starts at 0, 0 right there, that's in a sense an endpoint for me. Notice that if we take the fourth root of something, when does it hit the line y equals 1? Well, the fourth root of 1 is 1. So the nice thing for us right here is that this sort of like corner point on our graph is the same endpoint for both of our variables. It's at 1, 1 right there. And it's the same for this graph that's over here. So the point is we might want to set this up either way. I'm just looking, which way did I do this first? Yeah, I think I did this guy over here first. So in this diagram right here, got a little crappy right there. But what I can see here is that the thickness of this Riemann stick right here, maybe I'll just draw my Riemann stick. This has a thickness of delta y. This is the change in y value. This is y value stuff. It's the vertical amount. We're always going to get y stuff that's right there. What I alternatively would need to know is what is the x value, right? So this x value that I'm going to get here starts at 0 and it goes up to x being something. What is x really in this case? Well, I can get that information from this guy right here. X seems to be to me the same thing as y to the fourth. Do we agree with that? That we can take the fourth power on both sides to sort of rewrite this equation to be in terms of x instead of in terms of y. I now have an expression for what the x value is, but it's in terms of y, so that's going to help me do my integration. So remember now, when we set up our integral, if I'm thinking that this is going to be x stuff times y stuff, length times width is what I'm always thinking when I say x and y, length times width. It seems like we're picking here for our top-bottom thickness, y to be the infinitesimally thin one. So that's going to give us the dy over here. I then need a representation for my width, but it's really helpful for me to be in terms of y because we're doing an integral with respect to y. So this is my x information, but what is x in terms of y? It's y to the fourth. What bounds do we have for y? What values does y progress through in this entire graph? Y is going to go from its lowest point of 0 to its highest point of 1. So there's how I'm going to go ahead and set up that integral right there. Before I even do this one, let's go ahead and just set up our other integral and see what that would look like instead. This one's going to be a little bit different. It's going to be a little bit less nice for us here, but we do have very similarly, we have a vertical Riemann stick. This one has a width of delta x. This one has a height. It has a height of some y stuff, right? And what is y? Well, I know what y is. It's been given to me exactly right there. I know how to think about y in terms of x. It's the fourth root of x, or x to the 1/4. That's right there. So there's my Riemann stick. If I want to conceptualize this as adding up sticks horizontally across to get an area, the first example is adding up sticks vertically to get an area. In this case, I can set up my integral. It's going to be my x stuff. It's going to be my y stuff. Length times width is what I really mean when I say x and y right here, right? And in this case right here, it looks like what my x stuff is my x stuff is, my width is the dx here, right? And I'm writing this kind of not in the order that we typically write it, but that's irrelevant here. So come back up here now. So I've got my dx for my x stuff, the x component, the width of my rectangle delta x, the height. I want this to be in terms of x because I've got dx stuff. So my height is y, but I know how to represent x in terms of y. It should be x to the 1/4. And this is a weird way to write this integral, but it doesn't matter. This dx is multiplicative in there. So this is this guy now. Ooh, I'm actually realizing I actually think I'm making a mistake here. And the mistake I'm making is I think the question that we were asking yesterday, I'm dropping off a thing right here. Is the height of this rectangle the height of this curve? And the answer is definitely no. The height of this rectangle starts at a height of 1, and we are subtracting off the height of the curve, right? It's really that the height is starting the whole height of 1 minus the height of the curve gives us the remaining height of the rectangle out there, right? So what I'm actually thinking here, I should have been doing, is this should have actually been, it's all of the height minus the height of the curve. The total height is 1 minus the height of the curve gives us the height of the stick that we have between the curve and 1. Does that make sense there, right? So 1 minus the height that we're getting to from the bottom. It's really just the top minus the bottom is all I did right there. Top height is always 1. Bottom height is determined by x to the 1/4. So top minus bottom gives us the height of the stick right there. Right? So now I think down here, this really should be a 1 minus in there. And so now I think I really should be integrating 1 minus x to the 1/4 dx. This is my height of my stick. This is the width of my stick. And what x values, and since this is dx, I'm thinking what x values do we traverse? X values started at 0, x values went up to 1. So I'm going to get 0 to 1, just like I did over here. It's a coincidence that these are 0 and 1. This 0 and 1 is y values. This 0 and 1 is x values. It just so happened that this is sort of an overall square region right there for this one problem, right? So now let's actually evaluate these. We're expecting that we're going to get the same thing. We better get the same thing where we set these up to be equivalent ideas to each other. If I do this integral over here, the integral of y to the 4th dy, I know that integral should add 1 to the power. So I know this is going to be something like y to the 5th. If I were to take the derivative, I'd get 5y to the 4th, but I only want 1y to the 4th. So I'm just going to keep 1/5 of it. So 1/5 y to the 5th, evaluated from y equals 0 to y equals 1. Evaluated at the upper bound, we just get 1/5. Evaluated at the lower bound, we just get 0, and so we're going to get 1/5. Over here, for this guy, we can do a similar thing. Integral of 1 is just x. Integral of x to the 1/4, well, we're going to add 1 to the power. So 1/4 goes to 5/4. So I know I'm going to get something like an x to the 5/4. We've added 1 to the power. If I were to take the derivative of this, a 5/4 would pop down. I need a term that's going to cancel that because I only want to get the 1. So 4/5 seems to me to be the appropriate cancellation term right there to end up with one single x to the 1/4. And we'd like to evaluate this from the x value of 0 to the x value of 1. Again, when I plug in 0, all of this just goes to 0. So in this case, I really just need to do my f of 1 minus f of 0. And that's just, in this case, is just going to be f of 1. And it looks like that's just going to be 1 minus 4/5. And that's the same 1/5 that we're getting right there. So again, thinking of our Riemann stick, stopping and drawing not just the picture, but actually labeling the lengths of an individual, one representative Riemann stick is everything about how I know how to build my integrals smartly here. So drawing a Riemann stick diagram, I think is, and I should say, this is not necessarily a thing that I see like every other mathematician doing. I've seen some teachers that draw diagrams like this, but this is not like a universal concept of like literally drawing this one stick. But I really, this one stick is a valuable stick to me. So I think about that stick all the time right there, that one stick, real valuable stick. So let's talk through some of these other guys right here. So 47, this is not much of a math problem. This is a unit problem. What does this quantity represent? Oil leaks from a tank at a rate of R of t gallons per minute. So R of t is measured in terms of gallons per minute. So a typical thing is to use brackets to notate units, gallons per minute. So I know that R of t, whatever it is it's measuring gallons per minute. The other thing so that's my R of t term right here. The other term that we are multiplying it with, and again, keep remembering, this is all just x stuff times y stuff. This is all just a length times a width. So these all have units. These are infinitely small units of time, but units of time nonetheless. So when I think about what dt has going on here, it has units as well, and those units are time. And one would have to assume, right, this is in our same units that we are in. This is time. This is volume per time times time. So notice here that what we're doing, and when we do this integral from 0 to 20, this has to be time units because this is dt. Therefore, these are t values. So it looks like what's going to go on here is we're going to multiply lots of gallons per minute times minutes. And when you multiply gallons per minute times minutes, what do you get for your units? Is gallons. So what this looks to me like is happening here is if I were to describe this quantity of this integral, even though there's no function for r, so I can't compute it, I know that whatever we get out from this integral right here is going to be measured in gallons. And what gallons is it? It looks like it is the gallons that leaked from the tank from time 0 to time 20. Or I should say the number of gallons that leaked in the first 2 hours. Right? Since this appears to be measured in minutes right here. So I really like this kind of like what does this quantity represent problem, because this really forces you to keep remembering that each of these things has a unit. This is just a length times a width, and we should be able to do our little bit of unit math to find the resulting units. I think that this just like little look at units is, in a sense, the core concept of the net change theorem. It's that if you're ever taking the integral of a rate of change, dt, it's always going to be your numerator term that's remaining, because it's always going to be something like gallons per minute times minutes leaves you with just gallons. It's the accumulated gallons over time. Remember that integrals are sums, so you should be thinking of this as how much oil leakage have we accumulated over time. It's an accumulation idea here. So not much of a math problem here, but certainly interpretation that's like kind of critical to what we're doing right here. So you should certainly expect like something like this right here on a test or something like that. These next ones right here are going to talk a little bit about distance and displacement as we've done before. This 54 and 56 will feel a little bit like the problems that we did at the end of yesterday's lecture here. So use the velocity function to find the displacement and the distance traveled over time. And so the first thing I want to just do right here is exactly what we just did in the last problem. You should notice that if we do something like an integral of vt dt, that this is meters per second times seconds. So this is going to give us meters, right? This is going to give us our accumulated distance when we compute this integral, because all we're doing is adding up lots of meters per seconds times seconds. And that's just meters. We're adding up lots of meters terms. We're going to get a distance out of this. So what I'm thinking to myself is we should just be able to straight up integrate VT to find our total distance traveled. But what we're going to see is that we want to make sure that we understand this distinction between displacement and distance here. So let's stop for a minute and think about a graph. Every time in your entire life that you see a function that you have once graphed before by hand, you should graph it again by hand right now. This is something that you know what it looks like, and having a picture is going to help us out quite a lot here. So if I'm going to come over here and graph my v of t function, then I'm thinking to myself, I have t as my input, v of t as my output. I can factor this, I think, pretty easily in my head here. T minus 4, t plus 2, I think is my graph right here. So I actually need to extend this a little bit right here. I know this is an opening up parabola because that is a positive term right there. So I should have 4, there should be a point. At negative 2, there should be a point. And it should be opening up. Yeah, exactly. So, and meters is giving us position, right? That's a distance or a position. The total distance traveled, it's like the elapsed distance over that time, exactly. Adding up rates of change of distance per unit time is going to give us those distances. Yep. So we got our opening up parabola right here. And here's the important thing that we want to identify, right? There's my crappy parabola. This is going to go out to 6 for our time of interest. And here's the thing I'm noticing. We're interested in time 1 to time 6, right? So here's really time 1 to time 6. What I'm noticing here is from time 1 to time 4, we have a negative velocity. And I'm noticing that from time 4 to time 6, we have a positive velocity. So what we should be thinking to ourselves is when we distinguish between displacement and distance, like if I go to the grocery store and come home, my total displacement is 0. Thank you, Coffee Gopher. Yeah, this is the audio will be always our slight thing here. It is a little bit better because it's in my earbuds here, but hopefully it sticks with us here. Um, yeah, and once we've gotten through like a week of these videos too, I'm going to stop and like really see how these seem for everybody. It might be that I need to invest in some more things to help make this a little cleaner here, but it's obviously a little hard for me to judge those things. So, oh, I'm intelligible. My wife never says that. That's good. So our thing here, all right, we gotta distinguish between going forwards and going backwards. I think it's kind of good for us to picture sort of being on a wire here, right? It looks like what's going to happen is we're going to start at time one, right? So I'm going to draw a little diagram here. This isn't a graph. This is very much a diagram. At time one, we're somewhere in space. It's our starting time. It looks like at time one, we have negative velocity. So I'm picturing that as saying we are moving to the left from time one. And we're going to keep moving to the left until we have zero velocity. That's going to happen at time four. So at time four, we're going to get to a point. Notice that at time four, we're actually not moving. We have zero velocity at time four. Then from times 4 to 6, we're back having positive velocity once again. So we're going to head back in some direction, right? Now, I don't know if time 6 is going to leave us like earlier or later out there, right? But there's going to be some place out here where we're back at time 6 where we have moved back in this direction here. So I'm sort of making like a flow diagram. In a sense, this is sort of like a one-dimensional picture that requires me 2 dimensions to draw it. But I'm kind of picturing this is a little bit like going to the grocery store and coming home. There is in a total distance I traveled 2.5 miles there, 2.5 miles back. So my total distance is 5, but my displacement is 0 because it was sort of like I accumulated 2.5 positive miles away from home going there, and then 2.5 negative miles away from home coming back, which displacement in total then is 0. So to distinguish between displacement and distance, we need to know when are we talking about positive stuff and negative stuff here. And so let me make some more definitions here. Our total distance then should be, let's see here, we got distance. Distance is just the total distance that we traveled. So I'm picturing in this sense right here, this should be the absolute value of whatever happened from time 1 to time 4 plus the absolute value of whatever happened from time 4 to time 6. And the reason I'm writing, this is obviously terrible notation right here, but I'm trying to indicate to you that I don't want to care that this was in a sense negative distance that we accumulated from time 0 to time 4. It still qualifies as distance to me. So I'm just trying to add up all of our distance parts. On the other hand, our total displacement, that should really just be how far away are we at the end of this. So I don't need to worry about any of this absolute valuing right here. For the displacement, I really can just say, yeah, from 1 to 6, how'd that go for us? This will give me what my total distance is from our start at the end, and that's what displacement is. Distance involves adding and subtracting. Counting all quantities in a sense as positive, whether they're positive or negative, so absolute values. Displacement just says, how far away are you from where you started? And that's all, and we're going to get that out of just doing our straight up integral right here. So displacement's going to be a little bit easier. I think we can just do this one. I'll do my distance one in a second. We were given an equation here of t squared minus 2t minus 8 dt, and that's from 1 to 6. If I do some integration here, t squared I know is going to go to some sort of t cubed. I don't want to have 3 of them when I take a derivative, so I'm going to stick a 1/3 on it. Minus 2t, that's going to go to a t squared. If I were to take the derivative, the 2 would pop down, and that's exactly what I want, so I'm going to leave it. Minus 8. Integrals of a constant are always just going to get their linear term stuck onto them. The derivative of 8t is 8, and we keep that minus sign. Now we just got to go ahead and evaluate this guy from 1 to 6. So t equals 6 up top, t equals 1 on the bottom. And plugging in 6 into this guy, that's kind of a bummer right there. That 1/3 might actually help. So this is really like 6 times 6 times 6. But one of the 6's I'm going to write as a 2 instead. So 6 times 6 times 2. 6 times 6 is 36, times 2 is 72, minus 36, minus 42. That's everything evaluated at 6, minus everything evaluated at 1. That should just be 1/3 minus 1 minus 8. And if we go ahead and do this computation, what do we get? 36 and negative minus 42 is going to give me a negative 6 minus, and over here, negative 9 negative 8 and 2/3. So I'm going to end up getting a positive 2 and 2/3. Minus a negative, and so that's going to equal positive 2 and 2/3. And I should never write mixed numbers because we're all mathematicians here, so 8/3 is what I'm getting for my total displacement there, and 8/3. And again, I've got my upper bound minus my lower bound stuff. That's right there. Uh, oh, 40. Oh, I did 6 times 7 instead of 6 times 8. Uh, you're right. That's 48 right there. So we get 8 more, so that's actually a positive 2. So am I getting 10 and 2/3? I think that's the one that we're looking at right there. Yeah. I just did a little multiplication error as all that happened right there. And kind of whatever. These last two steps are certainly what I care about sort of the least in this class. I want to know concept stuff. Do we know how to kind of like differentiate between these two sort of tasks of distance and displacement? So let's take a look at this guy now. And this guy, what we want to identify is we would like to grab all of this area here. And even though it's negative area, I want it to contribute in the same way as my positive area over here, right? So this is really our overall area that we're gathering here. When we talk distance, we are considering this negative, we are considering this positive, and we're adding the positives and negatives. Or sorry, for displacement. When we talk distance, this is negative and this is positive, and we add them as the negatives and the positives as they're actually going to be for the displacement here. So what I want to do now is do the integral from 1 to 4 of v of t minus the integral, the absolute value of 4 to 6 v of t dt. And a quick thing that I'm noticing right here is that 4 to 6, it's actually already positive, so I don't even technically need these absolute values. I can see on my graph, I'm going to get a positive value. I just know that however much stuff I did to the left over here, I don't want to care that it was to the left. I just want to accumulate it as distance overall. So I'm going to do a little bit of reusing my old work over here. I already did this integral. I already did it. It's the antiderivative is sitting right there. So I think I could do, you know, my 1/3 t cubed minus t squared minus 8t evaluated from 4 to 1. This is what I'm putting absolute values around. Minus 1/3 t cubed minus t squared minus 8t evaluated from 4 to 6. Yeah, falling off my screen over there. So here, I don't even think that I'm actually going to finish writing this one out since this is going to take kind of a ton of writing, and I don't know that it's super valuable for our time. This is the concept. The reason I'm doing this problem is so that we can get this concept out there and attach this concept to the diagram that we drew up top up here. We want to be kind of acknowledging, are we getting positive stuff? Are we getting negative stuff? How do we kind of interpret that in the context of like a physics problem like this. So we're going to do another physics problem here in a second. Maybe that won't count as our thing here. But again, recognize that drawing this graph really helps. It's not super clear to me what's happening unless I draw this graph and say, oh, a change happened at 4. I guess that's kind of the other thing that's kind of an important thing to highlight here. The number 4 was never told to you as an important location on this graph in the problem. If we didn't solve for 4, we wouldn't have known that that was our transition point from moving to the left to moving to the right. We wouldn't have known that that's where our breakdown location would be here for these integrals, something like this. Yes, you're asking about are you asking about in displacement over here? We just did displacement, and this is distance. Yeah. So this stuff over here is distance, correct? This is our distance. And again, the distance traveled, this is like me saying if I went 2.5 miles. Oh, yes, okay. I see what I'm doing that's dumb right here is I think this minus sign, right? Is this what we're all unhappy about? Yeah, that's just a plus right there because we're adding distance. I don't know why I put a minus right there. I think that everything that you guys are saying in chat right now is all correct what we should be thinking. We know, and again, back to my diagram here, the distance from 1 to 4 was to the left. So it's a negative distance. By taking its absolute value, it becomes represented as a positive distance. The distance from 4 to 6 already was positive. In a technical sense, we maybe wrap it up in absolute values, but like I knew this one should be a positive number anyway. And I do want to add the distance from time 1 to time 4 to the distance from time 4 to time 6, even though they were in opposite directions. So we're doing the absolute value of each of them individually. I do think I said some small things wrong there, and that minus sign was certainly a problem right there. So I think I just said all of my things correct right there. Displacement, we just get to do the straight up integral. Displacement is really just saying what's the x distance between this dot and this dot right here, right? So the x distance, the overall displacement is good. Yeah, the minus sign was my incorrect thing right there. So distance versus displacement. Distance, we need to stop and think absolute value as broken down by all of our x-intercepts. So also, yeah, Chris, you're saying the right thing. The x-intercepts are key for us here. We got to know where our breakdowns live. If this was like a cubic function, then we might have needed to break this up into 3 different chunks at multiple different x-intercepts, stuff like that. Exactly. So conceptually speaking, displacement, you just get to do the straight up integral over the entire region. Distance, we need to do the sum of the absolute value of the integrals as broken down by our x-intercepts to make sure that we're always adding positive quantities to positive quantities. Okay, I think I said all that conclusion stuff right there. So again, I'm not going to finish evaluating this just because evaluating polynomials is boring right there. The big concept is exactly what we've laid out, and especially the very important addition sign in there. So let's actually do this one here, a little bit more of our doing of our associated with our definite integrals and evaluating some stuff here. This 56 is a really nice problem because this requires us to both do one definite integral and one indefinite integral, and so it's good to kind of help us think about what we've got. So what I'm seeing in 56 to get started here is the first thing we're given is acceleration information in an equation. What we're looking to find at the very end is distance. Yeah, Grave, these are all just homework problems from the textbook. I just found the good ones that I wanted. Yeah, these are exactly from the 5.4 section. So we're starting with acceleration. This is what we're given. What we want is distance. And what I know, because I'm a calculus person, is that in between is velocity, right? This is sort of the calculus in-betweener between distance and acceleration. So I'm thinking that we're going to work through velocity along the way. So we've been given acceleration information. We want to get to distance. We saw yesterday that we can do some things like, and again, if I write my acceleration is, so if we did an a of t dt, this is like me saying acceleration is meters per second squared. dt is time, so that's just seconds. Well, this is going to give me meters per second. That should be giving me v of t, right? So I'm just doing unit math whenever I'm thinking about how this integral derivative relationship works between position, velocity, and acceleration. Just doing some units. Acceleration is meters per second squared. Meters per second squared times seconds gives you meters per second. So it should be things like the integral of acceleration is velocity. The integral of velocity is distance. So I'm thinking that I want to do some of this because I know I need to work down the list in this direction towards distance stuff. I want to find a distance traveled over a time. That sounds to me like a definite integral. So let's go ahead and see if we can come up with a v of t equation here. So I'm going to integrate a of t. That should be my 2t plus 3 dt. This integral is pretty easy. Just doing some polynomial parts. Should be getting a t squared here and a 3t here. But notice that we weren't given acceleration over a time, right? That didn't happen here. This was just a general indefinite derivative or integral. So I'm going to go ahead and put my plus c on the end. This should now be my velocity because velocity is the integral of acceleration. I kind of want to know about c usually, but the good news is that they told me an initial velocity, right? They said that at time 0, my velocity is -4. So I should be able to say -4 is my velocity. Plug in some zeros here. And it looks like c is going to be -4. So it looks like I've really got a full v of t equation now, right? I really know that my velocity is going to be t squared plus 3t minus 4. I've got my full velocity equation here. Now I can use my velocity to get to distance. I can take another integral to get my velocity down to distance here. And notice in this case, rather than trying to come up with a general equation for distance, I specifically want to know how much distance was traveled over a given time. So this is now going to be a definite integral. So now I'm going to take our velocity information here and say, let's figure out how much change in velocity was accumulated from time 0 to time 3. So this should now give us our distance over the first 3 seconds of this particle's travel. I can now go ahead and integrate my t squared plus 3t minus 4 from t equals 0 to t equals 3. And by the way, notice that this is the last problem from the section in section 5.5. That's when I'm going to really start yelling at all of you about identifying our variables right there. It's your daily yelling for the day is going to be about the variables. And we've got our dt right there. I think I just want to push all this down here. And now we can go ahead and do our integration right here. I'm going to get a 1/3 t cubed plus 3/2 t squared minus 4t. So there's my antiderivative. I'm evaluating this at t equals 3 and at t equals 0. You should notice that every single time you ever integrate a polynomial, any constant term is going to get a t attached. And so anytime you have an integral of a polynomial and 0 is one of your bounds, that 0 should always zero out the entire thing right there, which is nice. Yeah, Grave, I did that yesterday, and I will continue doing that for sure for these as well. These documents will all get posted here. So again, I'm going to say here, or let's just call this f of t maybe. And I know that f of 0 in this case is 0. So I can say here f of 3 minus f of 0 is really just f of 3 in this case. So here it looks like we're going to get a 1/3 of 3 cubed plus 3/2 times 3 minus 4 times 3. And so that's going to be a 9 plus 9/2 minus 12. That's 4.5, 13.5, so 1.5. If I can do my actual computation correct, then I think we should land at a 3/2 right there. And again, this was evaluated at 3, mine is evaluated at 0. But if you evaluate this guy at 0, it just goes to 0. So I just didn't write out that part that's right there. So yeah, again, here we go. Keep on remembering our acceleration velocity distance relationships. And if you ever forget which way you're going, just think about what would happen if you did a of t dt. Acceleration times time, you know your units. You can do the unit math. All this is just a little unit cancellation to figure out what your quantities are going to look like after you perform some integration right there. Did I do this wrong again? 3 cubed should be 9. 3/2 times 3, 9/2 minus 4 times 3. I think I'm right, right? Oh, I see. Yep, it's squared. Totally. I see what you're saying. Man, I can't do my computation today. Holy cow. That's squared right there. So that should have been 27/2. And okay, now I should just write this out correctly then. Okay, thank you guys so much in chat. Yeah, the second term is squared right there. Thank you guys. You guys keep me on my toes there. Well, yeah, I'm doing it fast. I'm making all these mistakes along the way. It's okay, right? And honestly, guys, as I said before, I don't want you guys to think that answers don't matter, but man, solutions are what matter. All of your guys' work is going to look like this for all the pages that you submit to me for stuff. All the grading that I do, it all happens up here. It's certainly the case that if I just check and see 21/2, I'm pretty confident a lot of this went right, but man, you could miss the final answer on every problem this semester and still probably get an A in this class as long as I can tell that all of your thinking is good and well organized and your concepts are correct. So I'll be as lenient with you on the actual arithmetic as you guys have been with me here. So thank you for keeping me up to date with those guys. So there we go. So that's the last one I wanted to look at there for 5.4. And I've been going here for a solid 50 minutes. So we should certainly hop into some section 5.5 stuff here, hit some U sub concepts here. So this section is called the substitution rule. Nobody calls it that. Everybody calls it just U sub. The U is just going to be a generic variable letter that we're going to help use as an intermediary variable to help us do some stuff. So our couple statements here. Integration and differentiation, as we discussed last video, are almost inverses of each other, close enough that it seems sensible that for every differentiation rule, we should ask, can we undo that with an equivalent differentiate or an integration rule that goes the other direction? The most important differentiation rule is the chain rule. So hopefully we can figure out how to undo the chain rule since it's like the differentiation rule that comes up the most often. So here are some basic chain rule things that I do on like day one of chain rule with my students. We have our outside function of sine. So when I take my derivative, the outside function, we take its derivative and get cosine. We leave the inside function alone and we multiply by the derivative of the inside function, which is just 3. Similarly over here, the outside function is the exponentiation, and I know that the derivative of any exponent base e is always going to give me back the exact same thing. But since there is an inside function here, we need to multiply by the derivative of that inside function to accumulate its rate of change as well, right there, right? So some basic chain rule applications. So what our goal should be when we're trying to undo the chain rule is we want to look for any place that we see both an expression and its derivative, both sitting within an overall expression. So here I see an expression of 3x and I see its derivative of 3 are both multiplicatively members of the expression. I see the expression x cubed plus x, and I see its derivative, 3x squared plus 1, are both members of this. So when we're hunting to undo a chain rule, we're thinking to ourselves, do I ever see any place where I see both an expression and its derivative, both within the full integrand that we're looking at? If so, I should be able to undo some chain rule step right there. So let's look at a couple of easy first examples right here. So here we go, our very first U sub ever. What we want to do is we want to look for that chain rule type stuff that we know to expect. Hopefully this one here seems relatively easy to you, and I don't want to make you feel bad if you don't see it, so I put easy in quotes. But what I'm looking for here is I'm always asking myself, do I see any expression and its derivative both within the integrand? In this case, I see x cubed, and I see the derivative of x cubed, 3x squared. Both of those are in here. So here's the way that we're going to walk through this. What we want to do is we want to carefully undo our chain rule. So what we're going to always do here is introduce a new variable that's going to be like our in-betweener variable. Always, we're going to pick out the expression whose derivative exists, right? So not the derivative expression, but like the original function expression. In this case, the x cubed. Here we saw that x cubed and 3x squared were our expression and derivative. So I'm going to pick u to be x cubed. This is going to be my little helper variable that's going to help me get through this. So since x cubed and its derivative are in here, I'm going to define our helper variable u to be the x cubed. I'm going to go ahead and I'm going to take our derivative of u with respect to x, because what I'm going to want to do is I'm going to want to swap out all the x's in this expression for u's, including our differential term dx needs to turn into some form of du. And here's how I'm going to help do that here. This is going to give me a 3x squared right there. This is good because x cubed and 3x squared are exactly my parts. My problem is that this substitution is a little bit weird right here because I don't know that I want to be throwing in this derivative du dx. So there's a little algebraic thing that we do here, and this is going to be one of my shake my fist moments in this class. Du dx is not something that you should really be treating as a fraction. You should not think of du dx as a fraction. You should think of this as the derivative of u with respect to the variable x. This is one quantity. The reason that this notation was chosen for this single quantity was because it often ends up the case, but not always ends up the case, that treating this like a fraction ends up being equivalent to the actual things that are happening under the hood. This is just my long form way of saying, do not think of du dx as a fraction of du divided by dx, because it is not. But it turns out that our algebra rules are going to be equivalent to the true calculus rules here, meaning it is legal for me to do this multiplication of dx to the other side. The reason why this is really helpful for me now is because I now have the parts that I need to replace all of the parts of my current integral that I don't know how to do. What I can see here is that 3x squared dx, that's just what du is. So I'm going to swap out all those parts for just du. I can also see that I have an alternate expression for x cubed. It's just u. So this is just going to be sine of u. Well, that's way easier. Sine of u du, I can do that no problem, right? So this is a much easier integral to represent what we're interested in than this guy was. Our only difference is we want to get our answer back in terms of x, so we'll have an algebra step to redo at the end out there. But again, this 3x squared dx came together to form the du, and then we just swapped out x cubed for the u as we defined it to be. I know how to undo this. The derivative of sine is cosine, so the integral of sine should be negative cosine. So I'm going to get my negative cosine of u plus c. So I've done the calculus, right? The variable swap helped us do the calculus. Now I'd like to get back into x land where we started this problem, and that's easy. I just want to swap back out u for x cubed. Negative cosine of x cubed plus c. We get our plus c because this is an indefinite integral. We didn't get any bounds of integration. And now, of course, we should be able to check our answer, right? This should be my answer right here, but since we have derivatives available to us, we should always be able to check. If I take a derivative of negative cosine, I should be getting positive sine. I leave the inside parts alone. I multiply by the derivative of the inside. And this is a constant, and the derivative of a constant is 0. So it looks like we did get back our original integrand right there when we took the derivative, so I feel really good about this answer. So what u substitution is saying to us is, if you can find a expression and that expression's derivative both within an integrand, then we can make a change of variables happen that reduces it down to a much, much simpler integral that we can do. Once we've then done the calculus step, we can then go back and undo the algebra swap that we made to get back in terms of our original variable right there. These are both minus signs right there, no hyphens. That's the integral of sine is negative cosine. Thank you for that question. So there's our very first u sub right there. So now let's see that this doesn't always go perfect. In this case right here, we had x cubed, and we had exactly 3x squared also as a quantity that's in here. In this case, we're going to end up with something close, but not quite exactly what we want, and we're just going to have to make a small adjustment to fix it for ourselves. So again, I'm looking at this right away, and I'm saying, oh man, I don't know how to do this integration right here. So I'm stopping to think, because we now have one integration technique available to us, and I'm saying to myself, do I see any way in which I see both an expression and its derivative in here? And I kind of see that, right? It's not perfect, but I kind of see that. The derivative of x squared plus 1 is going to be 2x, and that's super duper close to just x right there, right? It's close enough. It's only within a constant multiple, and we're going to be able to handle that. So I'm going to do the same thing I did over here, and I'm going to say, well, the u should be the non-derivative part. That's going to be my x squared plus 1. I'm going to go ahead and do this. So, by the way, also, this block right here, I never write that. I always just go straight from this guy to this guy, the differential statement right here. It's just taking a derivative and writing each of the differential terms on each side right here. And again, you're going to do a whole bunch of these. You're going to get used to this as well. I'm going to take my derivative on both sides and write the differential terms. And so what I'm seeing here is I almost have exactly what I want, right? I don't have a 2x dx. I just have an x times dx in my problem. So what I might do for myself here is just divide by the 2 on both sides. And now I have exactly the component that I see in my expression over here to make my variable substitution happen right there. Yeah, I might have dropped a few more frames right there. And also for you guys that are mentioning the audio, the thing that I am noticing, and again, part of the reason that I'm streaming this on Twitch is because when my stuff gets streamed to Twitch, even if it ends up not perfect during the live thing, it reassembles at least the audio perfectly on the video that we get on the other end, and that's kind of my nice thing too, is that it doesn't give me the scratchy version. It eventually reassembles this into the proper thing for the video on the far end. So if anything gets below enough quality, at the very least, it will be better quality in the video that happens. So here's the way I'm seeing this. Another thing to remember here is that our dx term is multiplicative. In a sense, I think a lot of people feel this as like a label for like with respect to what variable, but this is a multiplicative term. Remember that this is actually giving us one of the dimensions of our Riemann stick right there, right? So this is like an x times dx. It's totally appropriate, although I always feel weird about it. There are definitely like tons of textbooks that would write this like this. I always leave my dx as a floater on the end out there, but there's nothing wrong with this phrasing right here. So the good thing that I can see now is it looks like I can now rewrite this integral as x dx is going to get swapped out for 1/2 du. And the square root of x squared plus 1 is just going to be the square root of u. So that's all correct. None of those three parts I would ever write like that, though. So here's, I think, our smarter thing to do. First things first, constant multiples don't affect integration. So a constant multiple can always get pulled outside of the integral. So that 1/2 is going to go for a ride out here. I always write my du's or my differential terms as like floaters on the end rather than as like part of a multiplicative fraction. Finally, I know that radicals aren't really my friend for integration. I always want to see this as like a power. And so I could rewrite this as u to the negative 1/2, right? It's on the bottom, so it's negative. It's a fractional power because it's a square root down there. So here's my simpler integral to do. I didn't know what to do for our first integral, but by making some substitutions, a change of variable, I was able to, in a sense, undo the chain rule that happened here. And now we can just go ahead, perform the integration, get back into X land. So as we typically do here, I'm going to keep this 1/2 floating for the ride, and we're going to say, what's happening here? So I see that we're going to get a power rule since this is just a power. So I'm going to add 1 to the power. So that's going to become a positive 1/2. If I were to differentiate this, I'd get a, okay, so you're going to have to blank out this 1/2 that's floating. This is not the 1/2 I'm talking about here. I wish that wasn't even a 1/2 right there. If I were to take this derivative of u to the 1/2, a 1/2 would pop down here, but I don't have that same 1/2 in my integrand. So I need something to cancel that 1/2, which would be a 2, right? So don't get your 1/2s confused. If I were to now take this derivative, this 1/2 and this 2 would cancel, leaving us back with 1/2 u to the negative 1/2 once again. It looks like all we're, forgot my plus c. Here we go. There's the plus c. I made it in there. So all I'm getting here is the 1/2 and the 2 are canceling, and I'm really just getting u to the 1/2 plus c. Always, we want to give our answer back in terms of the original variable. So it looks like our answer here is really just the 1/2 power of, or the square root of, x squared plus 1, our original quantity. Again, you can go ahead and just take the derivative and confirm your answer immediately. I think I can even do this derivative in my head. It's really a 1/2 power, so the 1/2 is going to get popped out. The power is going to get reduced down to a negative 1/2, which is going to really give me a square root term in the denominator. When we multiply by the derivative of the inside, we're going to get a 2x that's going to pop out. But rather than 2x, we just have a single x because we actually pulled down the 1/2 as the power on the outer step of our chain rule there. So the 1/2 and the 2 canceled, leaving us just with an x up there in the numerator. So again, it's easy to do the differentiation to check your answer. The integration is the hard stuff that's right there, right? So like, I would really encourage you to do the derivatives because it's a little bit of work for you to just be 100% sure that you're right. Seeing the integrals is hard. Doing the derivatives in general is much, much easier right there. So when you see some complicated integrals, one of your checklist items, one of your early checklist items is always going to be, do I see anything that looks like both an expression and its derivative in there? Because if so, u sub is the way to go here. Also, this variable of u, you could pick any variable that you want, but 99% of mathematicians on Earth just always use u. It's sort of one of those helpful things. When I see u, I immediately think, oh, they're doing u sub. If you did s for all of your variables, it wouldn't immediately give me that association. So you can pick any variable you want. It's just common practice to use u, and people call it u sub here. So let's go ahead and look at some things that are a little bit tougher here. One, I'm only even going to do one of these. I'm just going to do the second one with e. I don't even think of this as a u sub one right here. I just do this without a u sub, but I will write this out as the u sub that it is here. The reason I say I don't even remember that this is u sub is because the only thing that's happening here is a constant multiple is getting popped out. I know that derivatives and integrals of exponentials are always going to give back the entire original expression. There's always just a modifier. So in this case, I'm like, well, I know my answer is going to partially look like this, but if I were to take the derivative, I'd really get 3e to the 3x, and I only want 1e to the 3x, so I'm just going to keep 1/3 of it, and boom, I'm done. Like that's what I personally do in my head for this one. However, we could certainly write this as a u sub here and say things like our expression that's extra weird, the thing that makes this a chain rule is the fact that it's a 3x up there. So I could just do a u sub here. I might want to do my 1/3 du here and get a dx. Yeah. So if I took a derivative, it would pop down to 3. But my derivative should return me back to my original expression in the integrand. So if I take the derivative of this expression, The 3 will pop down, cancel with the 1/3, leaving me with a coefficient of 1, which is exactly the coefficient that I have sitting back in my integrand right there, right? The derivative gives us a 3. Therefore, the integral should give us a 1/3 because those are inverses. And dude, I do this also, like the first even 2 times I've taught differential equations was right after when I taught a bunch of Calculus 1. And man, to switch back and forth between differentiation and integration is tough. I like, the first time I taught diffie-q, I like took a derivative every time I took an integral. And I was like, oh my gosh, am I ever going to stop doing this backwards? But it's, all you got to do is remember one direction, and the other direction is just the backwards of the one direction you remember. Yeah, exactly. That's, I'll be doing the same thing too. So back at our u sub here, if we wanted to write this as a u sub, then now we get to rewrite this integral as e to the u dx just became 1/3 du. So this is really just 1/3 integral of e to the u du. And that's just going to be 1/3 e to the u, which is really just 1/3 e to the 3x, right? And I get my plus c's out here, but like, so this is just like our long form way of showing this. I kind of hope that you guys don't need to do a u sub for this. I hope that if I wrote like on a test, like show the work for this integral as if it's a u sub, you could like do this over here, but I probably wouldn't do that. Like I kind of think that this is simple enough that you can sort of bypass the formalities of u sub, but like these previous examples, I think are a little harder. Like I think you mostly need to do the u sub for these, right? Like I don't see this right away, or at least that one's maybe a little easier. This one's harder. I need to write all the stuff out for this one right here, right? I can't do that. This one, it's just a constant multiple that we're shuffling by doing the u sub. So maybe this is like the easiest u sub that there is. But again, if not, who cares? Just do the u sub and you're good, right? So let's take a look at some tough examples here. U sub is not hard to do, but it's hard to figure out when to do. I think the hardest part about u sub is being like, oh, now is an appropriate time for me to go ahead and do that technique right here. Let me get this separated, dang it. Can I not? Is that legal? Okay. Okay, here we go. So one thing that's bad about using Microsoft Word is it puts these in with my text and then moves them on me, and then I get all upset. So these are the harder examples, and the point here is that neither of these should look like u sub to you. If we're hunting for u sub, then what we're hunting for is a situation where we see both an expression and its derivative sitting inside of an integrand. And here I see x to the 5th and an x squared plus 1. Neither of these is the derivative of each other. Derivative of x to the 5th gives me x to the 4th stuff. Derivative of x squared plus 1 gives me just x stuff. Like, I don't know, I don't quite see where that's helping me out too much right there. Similarly over here, I just have tan x dx. I don't even see what my parts are. I only have one part. How can I have the derivative of it also being another part in there, right? So these I consider harder because the u sub isn't exactly slapping you in the face right here. It's not like, oh, there's my term and its derivative. I don't see them. So it's a little bit harder for us to kind of pick out the thing that we want to do here. So let's think, what do we do? Like, we're stuck here. And at least the one benefit that you get is this. You get the cheating knowledge that you're taking a college class right now, and that I wouldn't be asking you this question if it required a later technique, right? So this is one of those ones where you're like, if I knew that this was u sub, what would I do right here? We get that cheating knowledge of knowing that that's got to be what we're doing, right? So I don't see it. Like, that's just straight up my first thought. I don't see it. So I kind of have to like make a guess for myself. And here's the thing I'm guessing. The term in this problem here that bothers me the most is the stuff that's underneath the square roots is what's difficult for me to handle. Right? So I'm hoping that that's what I'm going to get rid of. And I'm telling you right now, I don't know where I'm going with this, but this is what I hope would be nice for me, right? If this is what I picked for you, I feel like that would at least make my square root term nicer, right? So now all I'm doing is following out an if branch, right? All I'm doing is being like, I don't know, is this what I should do? Let's see where this leads me here. If this was what I chose for u, then what my du would be 2x dx, right? That's just the derivative of this expression with its dx term. This is like du dx is 2x, and we multiplied the dx to the other side. So do I see any of these parts? Okay, one, I don't see the 2. So I think at the very least, I'd get some action like this. So in my mind, I'm thinking, can I get out my algebra beating stick and force this change of variables to be helpful to me? Let's try some stuff. I don't know. One thing I can see is this. I kind of want an x dx grouping. The dx here could partner up at least with one of those x's, right? So maybe I'm going to just rewrite this as like an x to the fourth, because I'm going to grab one of the x's to go with the dx on the end in a second. And my square root term, I can just call this u, which is at least a simplified term, because this is the square root of x squared plus 1. And on the end, I'm going to say I grabbed one of the 5x's to hang out with dx, so that it could be this term over here. So I'm going to write this as x dx, but really we're going to write this now as x to the fourth square root of u, and this is just 1/2 du. So here's where we're at so far. I've got my 1/2. This x is a problem, but we're close, right? In a sense, I mean, close isn't unfortunately good enough, but now my point to you is this. We're like almost there, right? Like we got our radical term into u land. We got our dx term into u land. Yeah, and Grave, people, I've seen this one being a pretty split camp on this one, whether it should be like the dx du, or sorry, the du dx and then the multiply, or just thinking in terms of differentials and just a du and just a dx. A lot of things in math, it's like, oh, mostly everybody does it this way. This is one of those things that's pretty evenly 50-50 split on how people like to think about it, not just students, but professors also. So do what makes you feel comfortable on that one. So again, my goal over here is to say I got I got 2 of my 3 x parts to get into U land. I just need to get my third x part, the x to the fourth, into U land. So what I'm thinking here is there any way that I can use this information over here to rewrite x to the fourth in terms of this stuff? And I kind of see a way that I think, and again, this isn't obvious, but so my earbuds did just shout at me. There we go. Okay, it's back. Okay, but audio's back? Yeah, it just turned off and turned back on. I don't know why it does that. I got to figure this stuff out. Yeah, we just got to the good part here, right? Yeah, exactly, Grave. So I want a u to the fourth, and the closest thing, or sorry, I want an x to the fourth, and the closest thing on my whole screen is x squared, right? So I'm going to get my beaten stick out here, and I'm going to say, what if we did this? Well, there's x squared. I want x to the fourth. Well, I could just square both sides. So this is my sneaky thing here, right? I'm really trying to force this substitution to happen here. And I used an expression for u and x squared to force an expression for x to the fourth in terms of u. And now I can make my final piece of substitution here. All right. So all of the u-ing I've done. I've finally put myself into a situation where I've converted this entire integral into u, and I don't know what to do again. So we're stuck again, right? Well, I'm gonna scroll back up and kill my bit rate. And I'm gonna remind you of an example that I very much cared to point out to you. Every time you're getting ready to do your calculus step, you should stop and then do algebra first. Right now we are ready to integrate, except I don't know how. So I'm going to stop and say, can I rewrite my integrand in a different way that makes this actually integrable? Okay. Boy, does it hate scrolling when I've got a bunch of writing on the screen. Okay, so here we are. So the point is, this still does not look integrable to me, but I can do some algebra. Remember what we said earlier. Anything that's like a polynomial is usually best written completely expanded. So I'm going to rewrite this as u squared minus 2u plus 1 root u du. And then I'm going to multiply it all out. So that's u to the 1/2. That's a u to the 2. And so now I'm going to do so I got a u to the 5/2 for my first term. That's 1.5, makes 3/2 for the next one. And 1, that's just a u to the 1/2. So we're here now. We're home. We just got to do a little integration, rewrite in terms of x, and we're done. So I have here now, let's see, we got to do an antiderivative. And so we're going to do all these undoings here, remember. So u to the 5/2, I know that this is going to become a u to the 7/2 because we add 1 to the power, but I don't want any constant multiple coefficients, so I'm going to include a 2/7 to cancel out the 7/2 that would pop down if we took a derivative. The second grouping, minus 2, this is going to be u to the 5/2, 3/2 plus 1 is 5/2. I need a 2/5 to undo the constant multiple that we would get from derivatives. And just notice that all we're doing is just picking out these reciprocals, right? All of my math here was just 5/2 plus 1 is 7/2. The reciprocal of 7/2 is 2/7. So that must be my constant multiple that I need to undo my chain rule right there. Our third term is 1/2. I add 1 to 1/2 to get u to the 3/2, but I need to get my reciprocal fraction here of 2/3, so that if I were to take the derivative again, 3/2 would cancel with 2/3, leaving me with 1 as my coefficient again. We're taking a half of all this, so maybe here's what I'm going to do here to indicate my 1/2. Half, 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 half. I applied that 1/2 to everything. Our very last step, just make sure you get back into X land. I got to scroll. I don't even remember what X was at this point. I got to go back up and look. Oh, yeah, I've got all my U stuff. U was X squared plus 1. That's the sub I need to get back out of U land. U is X squared plus 1. So it looks like my final answer here, oh my gosh, hang on, got my plus C. My final answer here is going to be, I've dealt with the 1/2, so I've got 1/7 x squared plus 1 to the 7/2 minus, I've still got left here a 2/5 x squared plus 1 to the 5/2 plus 1/3 x squared plus 1 to the 3/2 plus c. And boy, is that a gross thing to get at. And again, this is a great example of, even if you can sort of see undoing the chain rule in our first couple examples, there's no chance that you just saw anything that looked like this in your head on this example here, right? Like, we got to let the U sub drive it for us here. So this is a hard example. By the way, I do think this is a direct book example. I think yeah, this is, by the way, this is example 5 on page 417. And I've got, so you can check, like I have my answer exactly matches the book answer right here. I'm at least confirmed that way right here. So if you want to see any of the version of this, this is example 5 on page 417 right here. So again, great example because this chain rule is not, or sorry, the chain rule, the U sub is not obvious. All I did was I just tried something. I just hoped that this would be my U because that square root term looked like it kind of sucked. And I just saw, I was like, what could I do? Notice I wrote some things like this integral right here. I really don't like this expression right here because I don't like mixing X stuff and U stuff. But this is an intermediary step. I mean, this was helpful for me to say, like, where am I at so far? Oh, I only have X to the 4th to deal with. That led me to my idea of maybe I could rearrange my expression here and get an X to the 4th out. So this is some trial and error. This is like an explorative technique in a sense because these aren't always going to be super obvious as to what you should do. I want to briefly talk about the tangent example right here. Let's look through this guy. And what the important thing with this one is we actually get some choices. So again, this is one of those situations where you should be able to easily say to yourself, like, did we ever take a derivative and get tangent? The answer is no, so I don't just know an antiderivative for this. It's not obvious what the integral should be, and so my question to you should be, think back to trig class, and in trig, every time you had to deal with tangent and you didn't know what to do, what did you do instead? And hopefully your answer is you rewrote it in terms of sine and cosine. Oops, dx, right? That's always our thing to do. Sine and cosine should be your happy place for trig stuff, right? Like, why deal with secant if you can just deal with cosine? It's good to narrow it down. So now the thing that I have to think to myself is, again, if I'm thinking u sub, I'm hunting for a term in which that expression and its derivative are both contained here. And so what should I pick for u? And the funny thing about this one is, what's the derivative of sine? Well, it's cosine. So I could pick u to be sine and then let du be the cosine, and I got my parts maybe. Is that going to work? Can I do that? Let's try this. So if I do u equals sine, and then I should be getting du equals cos x dx. You should sort of feel good about what we just did. But this isn't actually going to work out. And I want to make sure that we see why. And the very unfortunate thing I did right here is make a little scratchy mark right here, this dx. What's really important for you to notice in this example is that dx is a multiplicative term as part of this integrand. This dx, technically, if it belongs anywhere in this fraction, it belongs in the numerator. I do not have a cosine x times dx in this integrand. I have a cosine of x in a denominator and a dx in a numerator. They are not together by multiplication. They are related by division. So I don't have this term or any real good way to get at it. So this is so close to exactly what we want to do, but it seems like it didn't quite work out for us here. So it looks like that didn't work. So let's try it again. What I'm looking at here is the same thing. I'm just rewriting this. So exactly. So it looks like what our other option here should be to pick the other one, because the derivative of sine is cosine, the derivative of cosine is sine. The only way that those things differ is just by a negative, and I can deal with a negative. That's not a problem here. So let's just pick the other one. So u equals cos x. And in this case, du would be negative sine x dx. Well, that's easy. I'm just going to move this negative over here. I'm not even going to write a new line for that one right there. And it looks like I should be getting at here, the u is what's on the bottom. Sine x dx, that just turns into u. So it looks like what I'm getting here is 1 over u du with a negative. The negative du was really the sine x dx. The cos x on bottom just became u. Now, I think I know how to do this. When we took a derivative of something and got 1 over, that was a natural log that we were taking derivatives of. And if you remember your technicality for this, it technically should be absolute value right there. I'm not too worried about that one. But now I can just go back into xland here. U was cosine of x for us. So I'm thinking here our answer should have been negative natural log of cos x plus c. In my head, the derivative of natural log is 1 over the inside function. That gives me 1 over cosine times the derivative of the inside function. That gives me the sine. So we get the sine parts over the cosine parts to give us the tangent parts right there. So not obvious that that should be our result right there. But if we stop and write tangent as sines and cosines, then we can try a little bit of our different options for u sub. Exactly. So Coffee Gopher just said the great comment right there. And this is kind of like the highlight that I want to pick out. What's going to happen over the next couple of weeks here is that I kind of pointed out to you guys, like chapter 5 is like basic integration techniques. Chapter 6 is basic integration applications. Chapter 7, advanced techniques. Chapter 8, advanced applications. We're going to kind of build up a toolkit here. And it's going to be the case that when you see a tough integral, you will have no idea what to do. And so you're going to want to walk down this checklist and say like, well, maybe this would help. Maybe this would help. Maybe this would help. Coffee Gopher's comment here says, looks like we're incentivized to put u terms in the denominator, considering how we're looking to cancel out the dx. And so I think just the only part that I would say that goes with your statement right there is it really matters that you don't put like a du term in the denominator, right? In our first example up here, we tried to do this, but we would have ended up with a du as a denominator term. And that's what screwed us all up right there, right? So with a lot of these things, I totally agree with you, Coffee Gopher. You want to stop and think like, Well, are my parts going to end up in the numerator or denominator? Is that really where I want them to be? And that might inform your decision about selecting which is the u, which part you're going to try and make the du. I think that I don't have to scroll. Coming back to examples like this, if we would have seen this as something like an x to the fifth divided by x squared of x squared plus 1, then we would have had to have stopped and thought like, ooh, do I want to grab u to be denominator terms or u to be numerator terms, stuff like that. And by doing a bunch of practice, you're going to feel out a bunch of general rules like this that aren't always rules. So they're not usually listed as a rule anywhere, but they are things where it's like 90% of the time you want to choose the denominator term to be u so that your numerator is the du, stuff like that. In chapter 8 or chapter 7, it's going to be really helpful that we kind of stop and make like a checklist of like, I found an integral I don't know how to do. The first thing I should consider is this. The second thing I'll try, like, and you'll walk through like a checklist of like things to try out there. So here's some tricky ones. And again, the point is rearrange some stuff, try things. It's okay to try stuff and be wrong. Just try the next thing. There's really only a finite number of combinations of things that you have to try here, right? Like there's only so many terms here for us to try, right? So I do want to look at, I think these are my last two examples right here. We're at an hour 30. I maybe just want to do, I don't know, I like 63 better, but you should all definitely be able to do 57. Maybe just for time's sake, I'll do 63 right here. I'll at least do it first if you're looking to wrap this up since we're at hour and a half is kind of what I expect these videos to pan out to be. In my head, they're going to be an hour, and I almost always talk for 50% longer than I manage to want to in every situation in my life. So I think this is about right. So let's at least do 63 here. If you guys really want me to do 57, I will, but I think these get at the same kind of big concept here. And 63 has a little extra something something in it for us right here. So 63 should feel like the tough one. Greg, you're asking about the textbook. So what's your question about the textbook? Because the easiest way to just get the textbook is to rent the one from the CR library, and they should have enough. Buying the book is probably a good idea because this is a good book. Like I still reference my undergrad calc textbook because it's different than the one that we use here. I like them both for different reasons. It's a good reference book. Calc 3 will almost definitely use the same book. Different editions. Okay, that's a good question. Maybe, yeah, let's talk about that in office hours because the reason that we do the edition that we do is because we want things to say cheap, but now this edition is so old that people can't even get copies anymore. And so that's turning into a problem. So it's, there's a pro and a con to all these choices that we make out there. So yeah, talk to me. If we can finagle a way for a different edition to work out for you with minimal effort from us, then that's okay. So hit me up in office hours and we'll chat about that guy. So let's look at number 63 here. And so again, no problem. So our one difference to notice is you should notice that we're doing a definite integral. We actually have bounds of integration here. So that's a big important part of this. The other thing that you should notice is that there's not a huge obvious choice of u. So I've finally decided what I actually want to do here. Let's at least state our u and du setups. I'm not going to do this whole problem, but let's at least set up the u and the du. And this guy here, I'm looking for an expression and its derivative to show up in here. The thing that I'm seeing here that's very helpful for me is to think of this integral here as maybe something a little bit different as e to the 1 over x times 1 over x squared dx. And writing it this way kind of helps me see that the derivative of 1 over x squared is going to be the derivative of 1 over x is going to be like our 1 over x squared term right here. So sometimes just writing your expression different is really helpful because it separates your components that you're trying to identify as like a u and a du and stuff like that. So in this case here, I'm thinking that I see that u is 1 over x. That should give me that du. We know that this is like x to the negative 1. So our derivative says subtract 1 from the power, pop the power down. So negative x to the negative 2 du, also known as negative 1 over x squared du. So it looks like then we can rewrite this integral as integral from, oh my gosh, so importantly, x is 1 to x is 2 of e to the u du. And it looks like all I got to do is pick up a negative to make all my other parts match up right there. So I'm not going to finish this one right now because I'm going to do the important thing that matters right there over here, just for the sake of time. But man, those are x numbers. Those are not u numbers. This is all u stuff. That's x stuff. You got to watch that. Let's do the one over here because this is just a more exciting integral overall. The one reason that this one's more exciting is for the exact same reason that our previous hard one was exciting, is because I don't see one thing that's a derivative of another thing right here. But again, I'm going to say like the square root term is more of a problem for me. So I am going to hope that this is a smart move for me to make, because that square root seems like my most annoying term. If I did this, then all I would be getting is just du equals dx. So I can ask myself, like, what did this really do for me, right? I'm going to do the same things I did before and say, well, where am I at so far? Well, I don't have an expression for x. Underneath the square root, that's just u, and dx is just du. Those derivatives are the rate of change. The slope of this line is 1, the slope of this line is 1. These are the same differentials right there, right? So as with before, I've got sort of my like stupid mixed integral here where we've got x's and u's mixed, but I'm close, right? I got one of my terms, I got my differential, I just have this standalone x. So now I come back over here and I say, is there any way that I could get x in terms of u? And there totally is. I can solve this guy for x real easy. Here we go. I have a way to write x in terms of u now. So these sneaky little algebra tricks turn out to be really important. Making things look different matters. And so don't just take things the way that they're handed to you. Rewrite things in ways that it's useful for you to see them. And as I'm literally saying that phrase, I'm starting to write a square root symbol. And I know that square root symbols are not my friend inside of integrands. So I'm going to write this as a u to the 1/2 du. And now we're in our happy place. But, oh my gosh, these are x values. Right? Don't lose track of this. That's x is 1, that's x is 2 right there. So I'm going to ignore this slightly for right now, or I should say I'm going to do this two different ways. There's two different things I could do to complete this problem. One thing I could do is I could do my integration in u, convert back to x just like we've been doing, and then evaluate over these x bounds. A second thing that I could do is I could convert my x bounds into u bounds because I know how x and u are related. I could then just do this whole process in u and never go back to x. I'll do it both ways. My antiderivative here, I'm going to leave this one in terms of x, from x equals 1 to x equals 2. I can multiply all this out. I'm going to get u to the 3/2 plus u to the 1/2 du. I'm going to keep reminding myself that these bounds are x values and not u values. Oh, wait, except that I don't need to write that right there because I'm doing the integration. Okay. So now we're doing the integral. Add 1 to 3/2 to get 5/2. If I were to take the derivative of u to the 5/2 with respect to u, I would get a 5/2 that would pop down here. I just want a 1, so I need a 2/5 to cancel it. Similarly here, add 1 to 1/2. I'm going to get 3/2. Oh my gosh, I just wrote that all stupid. Let me try that again. U to the 3/2. And then if I were to take the derivative of 3/2 to get back, I would get 3/2 u to the 1/2. So I only want to keep 2/3 of that because I want one copy of it right there. We don't get a plus c because we're evaluating this guy from x equals 1 to x equals 2. So super importantly, I can't do that evaluation because I don't have any x's. So in this setting, I've got to convert back into x land. If I scroll up, I can see how to do that. U is the same thing as x minus 1. So I'm going to convert back into x land here. U is the same thing as x minus 1. So 2/5 x minus 1 to the 5/2 plus 2/3. Oh, nope, not a u. We're doing x's. We're doing x land. 2/3 x minus 1 to the 3/2. And we're evaluating this from x equals 1 to x equals 2. Now, the book picked some really nice numbers for us here. You should notice that when we plug in x equals 1, we get 0 for the whole thing. So when I evaluate this from my upper bound minus my lower bound, the lower bound is just 0. So I'm going to go ahead and again discard it. Again, notice the book is setting us up with something really nice right here. When you plug in x equals 2 into each of these values, 2 minus 1 is 1, 2 minus 1 is 1, 1 to these funky powers is just 1. So I'm really just getting for my answer here 2/5 plus 2/3, and then it's like minus 0 plus 0. And so what are we getting here? 15ths. So 6/15 plus 10/15 is 16/15. I think is what I'm looking at right there. Yeah, so Coffee Gopher is now suggesting that he's seen this done the other way, right? And I kind of go back and forth on this. Sometimes it's easy to do it one way, sometimes it's easy to do it the other way. Our other option here is this. What we could have done is we could have taken these bounds of integration right here and converted the bounds. If x is 2, then I know, I can kind of scroll up here to see my little helper. If x is 2, then u is 1. 2 minus 1 is 1. Similarly, if x is 1, that's equivalent to the bound. If x is 1, 1 minus 1 is 0 for u. So what we've done now is we've converted our bounds of integration of x into bounds of integration that are u. Oops, equals 0. U equals 1. U to the 3 halves plus u to the 1 half du. So this is good. Yeah, exactly. I go back and forth. I don't always do this the exact same way. So notice that this one requires us to pop back into xland, but it didn't require us to change our bounds of integration. This route requires us to change our bounds of integration, but now 100% of the problem is in u, so you can just wrap up in u land. You're still going to get the 16/15. You're just never going to see another x at this point on for the rest of the problem out there. So the whole point of this really is not that one or the other is better, it's that you need to keep track. And so every time that I write things like bounds of integration that literally list the variable and not just the number, that's me being smart and keeping track of my variables, right? So this is where I'm yelling at you, don't lose track of your variables with definite integrals. What I mean is we all understand 1 and 2 to be x values when we see this original problem. But if you were to write right here just a 1 and a 2, any mathematician on earth would interpret the 1 and 2 to be u values unless you wrote the x's and had the known relationships. So this is like, if you're doing a change of variables, then that is adding on to you like a layer of responsibility to properly manage those variables. So when we create a new variable, be smart with yourself and write down what values are what variables each time that you're doing it. Um, Yeah, good, great. I do value that, and I do know that like I am thinking that I think more than half of all the students in the class have got like the goal of Calc 1 is always to end with U sub, at least like College of the Redwoods. Like that was my goal, my previous college and here, like Calc 1, like the goal is like get to U subs so that people have seen some integration. I know that not everybody got there last semester. I am hoping that for a bunch of people this is review, but this is a big time one of those things where perspective matters. The way that you look at the problem is going to heavily influence your route through it. And so seeing how other people do stuff is really valuable. To that end, since I'm wrapping up right now, I think one of the other pitches I'd like to make is I did post in our Canvas that there is a Discord that has been created for our class by one of our students in chat right here, which is great. Discord is a really good place for you to see how other people are doing this problem because you guys can just all go talk about your homework problems in there. You could take pictures of your work and just post it and be like, guys, I'm getting this one wrong. Does anybody see what I'm doing stupid? If you don't want to ask me, ask your your other classmates and see what's going on all the time. And especially once we're now into like these upper level classes, especially, and like I said, I haven't taught Calc 2. I know it'll happen this semester. Every single Calc 3 and differential equations test I've ever written, I've like made a key and then seen somebody do a problem like half the work as I did on the key. And I'm like, oh my gosh, like I did that problem like wrong and I got the right answer, but like I did it a way that took twice as much work because somebody else saw something that was better for that situation. So like there's always some perspective things to learn, even if you're a calculus badass. I guarantee that there's things that I do that are a huge waste of time and effort and thoughts on my end that could be done more simply. And it is very consistently the case that I like learn different ways to think about things in other settings. So like keep looking at other people's work. Oh, it's invalid. Okay, that's fine. I think I can easily. I think I was made an administrator, so I should be able to create a new link. Discord links do expire typically after a period of time, but I think we can make one that lasts for a longer period of time. So I'll change the link and I'll mention in Canvas that I updated that so that you know that it's the updated link right there. Thank you guys for pointing that out for me. And so I think the only other thing that I have to say here The last thing, by the way, you guys will learn that at the end of every lecture, I will have 7 last things to say that I say all of them are the last. That's how I roll. Last thing to look at right here. I don't feel like this requires any of my like time in lecture video right here. There is a very important concept of symmetry of functions with integration at the end of the chapter, at the end of the section. But I also think it's a pretty easy idea. It's a very important idea. So it's not like it's not important because I'm not going to talk about it. I'm just not talking about it because you're going to look at it and be like, oh yeah, I can see that picture. Those halves match, so you could do that. And in this picture, the halves are the opposites, and so they cancel. And okay, I got it. It's a pretty. I think it's pretty easy. Got problems with it? No problem. You can ask me questions, but certainly don't skip over this as the last idea in that section right there. It doesn't matter, but I don't think it's going to blow your mind. It's just another route to a shortcut that we can take with integration. And as promised, I always have a million last things to say. My last thing to say is this. You should immediately get used to the idea that there is no such thing as integration ever being easy. Right now, what we're doing is we are learning the easiest integration technique that we're going to get all semester, and it's kind of hard already, right? So, like, just remember that there is nobody on earth for whom they're like, oh, yeah, no, I'm good at integration. Integration's easy. Literally, not a mathematician on earth that says that. Most mathematicians on earth are like, derivatives are easy and I can do any derivative. You know, we host and co-host with Humboldt State University an integration bee every year, which is like a spelling bee but for integrals. And the reason that got started is because like MIT and Princeton started an integration bee like in the 70s, because even for students that are like, you know, the math majors at MIT and Princeton, even for them, it's still known that integration is like the classically difficult thing in upper level math. It doesn't ever like get easy. You just keep learning more techniques and new strategies for thinking about things. So keep looking at other people's work, keep having this perspective that like, since integration will never be easy, you always want those little helpful hints and little tricks. And like symmetry is like basically a trick. It's going to help take the workload off of some difficult things. So like every trick is important because integration is never an easy topic. So keep looking into those things. Keep using each other as the resources. You guys that have been in chat, I really appreciate it. Even if it's you pointing out that my audio is skipping all that stuff, I always want to know those things. So I do, again, really appreciate you guys being active in chat. We got 10 people in chat right now. That is awesome. And as people, I think, start to kind of feel out what we got going on this semester, that'll go up and down. But yeah, so recommendation of place to practice math outside of the book or My Open Math. Super good question. So let me point you real quick towards a different resource here. I'm going to pop on over. I think I still got audio here. Let me bring up my browser. Let me point out an alternate resource for you here. And then I could just obviously link to this in our Canvas page as well. In my statistics class this semester, we're using a book that is from the OpenStax series. So an alternate reference for like just an entirely other calculus book is you could go to OpenStax, which is stacks with an X. And this is Rice University, which is like a really good school. They have like this entire program where they're trying to like write full-time, permanently free textbooks that are like actually good for like a wide variety of subjects. I am using their book for statistics. I have not started using it for calculus yet, but they do have the full calc series sequence on here. I think they just call it volume 1, volume 2, volume 3. Oh, you didn't like the OpenStax? Okay, and you use that for Calc 1? That's good to know. I need reviews for these things. Yeah, no, and it's always good to just have a second resource for things that are out there. I am generally always assuming that people know about things like Khan Academy. That's always good for alternate video resources that are out there. And really, like, another thing I can easily do is just also say, because I think kind of another thing I want to do is just say, like, even if it's homework problems I'm not collecting, like, for example, we just went through, you know, a bunch of textbook problems. Like, these were just like homework problems in the back of the book. So maybe a thing I should start also doing is saying things like, you should go to the textbook and try these 4 problems. If you can do those 4, I consider those to be like the challenge problems from this section. And if you're good with those, then I'd say that that means you should be confident in your skills. So maybe what I could do is, even if it's not things that you're submitting, just sort of say like, I kind of consider these to be like the bar that you should be trying to achieve for an individual section. Yeah. Oh, Amber didn't like it either? Okay, that's good to know. I've heard only good things about the stats book, and I can't imagine that all their books are equivalent right there. The OpenStax format is nice. That's at least true. Maybe their content has something to be desired. So whatever, we'll see. It's good. You're asking the right questions. It's like it's good to have another resource. And I mean, another thing I can tell you is like I used one calc textbook when I was an undergrad. I used a different calc textbook when I was teaching in Colorado, and I am using a third calc textbook now here. It's really nice for me to have access to all those, at least especially as a professor, because like, I mean, when I'm going to write tests and stuff, I just bust open a calc textbook that I know that none of my students have, and I just get to pick out some other fresh problems from there and different ideas. And actually, to that end, there is going to be one section of content this semester that our book does not cover on how to find volumes of objects. That's just a different way to think about it that I'm probably going to snag out of a different textbook that does cover that. So, like, some of these things, there's just different material in some of these here. So, um, yeah, Khan Academy does have the good practice stuff out there usually too, because there are good videos that help out with that. So if you guys want that kind of stuff, keep communicating with me. I'll obviously always post it so that it's available for everybody. But yeah, Calculus by James Stewart is what we're using here. It's the textbook name here. Early Transcendentals. I hate it when they put stuff like that in textbook nicknames that don't mean anything to anybody, since I'm pretty sure none of my students know what a transcendental number is. I barely remember the definition of transcendental. So um, Con, it's cool. In any event, yes, hunting for extra resources is a thing. And maybe, all right, I'm going to say it for the billionth time this lecture now. Maybe my last thing to say is you guys are going to do your weekly writings for me. If you guys are finding resources that you find are particularly good, then that's exactly going to satisfy a week's worth of weekly writing for you to say, oh, I went and looked at these videos in Khan Academy and they were helpful to me for this reason. That can totally satisfy your weekly writing about like an external resource that you use for the class. And when people tell me about good resources, or what I really want it to be like is if you do the weekly writing for external resource, that when you write about it, it should be like you're writing about it to tell everybody, not to tell me. Like the whole point is that we can like share these. So I'm kind of hoping that the if anybody's weekly writing is about an external resource that you found, that'll maybe just get all like posted in one big page. Um, Cam scanner for the photo to PDF apps. I agree with you that feel like most students have been finding Cam Scanner to be the best. Like I said in my thing, I've been using the Adobe Scan. I've heard some people say that hasn't been working out as smoothly for them as it did for me. And it's, as I said in my message, it's one of those like tech things where like I don't know what's going to be best because I don't know like what cell phone you have kind of thing. So, but I agree with you. I feel like most students have told me that Cam Scanner is the one that they have been finding that's been good. So, um, oh, Cam Scanner sends it directly to Canvas? Oh, awesome. Oh, very cool. Ah, gotcha. Oh yeah, and good call there. If the iPhones do have a PDF scanner already built in, which is a good call on that one right there, which is nice. So cool. Okay, I'm gonna wrap it up now. So this went a little long. I'm not gonna try and worry too much about my time lengths on these videos here because I don't want to feel like crunched. But 2 hours is getting to be too long here, so I'm gonna try and keep these down to the closer to the hour and a half mark for these. And again, thank you guys for being in here for chat. I do appreciate the interaction with this stuff here. So, and we'll keep up with the resources and stuff like that. And again, if you find a resource, put it in your weekly writing, and we'll get that all collected for the class. We'll update the Discord link and I'll get that posted in there as well. We've got office hours coming up the next 3 days. If you guys have any questions for me, hit up those Zoom links there. I'll be there. Otherwise, email me for things that you got. Bring it. But it's good to have them in chat, especially if I'm making mistakes during lecture and stuff like that. I don't really have a problem with you asking here. It might be that I defer and say, let's talk about that in office hours, but you're always welcome to ask those in chat because a lot of times I just forget to say things that I do want everybody to hear. So you might as well bring them up. So, and I got to post the homeworks also for 5.4 and 5.5 as well. That's my other task. So I'm going to update the join link for Discord and post the My Open Math homeworks. And otherwise, I'll be in office hours if you guys got more questions. Thank you guys for being here. And next video lectures will be on Monday and Tuesday at